All right, so what we have talked about for review is some of you have asked about reviewing all the series tests. Well, let me just do limits here real quick. Before there's limits, or before there's series and ratio tests, we had the idea of limits. And the limit helped us to analyze these series tests a little bit. Limits are y values. We've talked about that. And the number one technique is if you get an indeterminate form, 0 over 0, infinity over infinity, infinity minus infinity, 1 to the infinity. Was it infinity to the 0? Was that one of them? I'm not sure, but there were 6 of them total. But these are the most common 4. 1 to the infinity is your definition of E. And you are finding y values by first identifying that and then saying, okay, once you have that, then you can say that the derivative of the f of x over derivative of g of x will work. Some key, maybe you've forgotten these already, but if you do the limit as x approaches 0 of sine x over x, that'll be 1. Limit as x approaches 0 of cosine x. But you can prove all these with L'Hopital's if you needed to. Don't forget the reason for looking at limits is it helps us to analyze continuity, which is the limit on the left has to equal the limit on the right, and the limits have to equal the y values. So the 3 parts to proving a limit is the y value exists, the limit exists, left equals the right, and the y value equals the limit. All right, so once we look at all those limits, continuity is limit on the left equal limit on the right. That's the limit. Continuity is the limits equal y values, and both exist. For differentiability, it's same thing. You have to have continuity, and you have to have the derivative on the left equals derivative on the right. Put your hands together like this. This is or is not differentiable. Non-differentiable. It's a cusp. How about this? No. How about this? Even if it's a little break, it's not differentiable. It has to be perfectly smooth sailing along there. Think of a longboarder, having a longboard on that surface. You'd have to do that. Okay, so then let's see. I'm so hip bringing in longboards. My son rides them, so that's how I know. Okay, so if it's differentiability, that's the key for Rolle's theorem. So differentiability means smooth sailing. And if you take 2 y values that are equal, y equal to a, y equal a, what's the slope between those two? 0. So if it's differentiable in between, it's proven by Rolle's theorem that somewhere there's a slope equal to 0. In this case, it's going to be a min. Mean value theorem is if these points aren't the same y's. This is like y equal to a, and this one's y is equal to b. You know, they're different. So then that slope somewhere, if it's differentiable, no cusps or any vertical asymptotes, somewhere the slope between those two has to equal that. This is new that's on the IB test option 9. Take a look at fundamental theorem of calculus. Derivative of the antiderivative equals f of x. We also had that other way around where you took the integral last. You'd have f of x minus f of a. Okay? But that's not what you were asking about. You were asking about these, the tests. So here's what you do. Start off, the first key thing is take the limit as x approaches infinity. If that thing is 0, you got a shot. If it's not equal 0, it diverges. Done. Then take the ratio test. Ratio test next. If you do the ratio test, this is here, u of n plus 1 over u of n, the limit as n approaches infinity, you're going to get a value of, we called it L, they called it C. The assumption is all positive terms. That's because if it's continuous or convergent, that C is going to be less than 1. But what's it greater than? If it's less than 1, it's got to be greater than 0, right? So that's why we say all terms positive, because it goes from 0 to 1. Divergent if it's greater than. Done. If it's divergent, that C is greater than 1 or L greater than 1, you're done. But this is the bad news. If it's equal to 1, then you're going to have to do one more test. And that test is probably the integral test. Integral test has 3. Positive terms decreasing on the interval and continuous on the interval are the 3 assumptions for that. If your integral goes to infinity, it diverges. If the integral gives you a value, then it's convergent. Okay? So that's the role. You go 1, take the limit. If it's equal to 0, then go for the ratio test. There's 2. If you do the ratio test and you get 1, you got to go again. Integral test. And if that integral test gives you a constant, then it's going to be continuous. Now we saw one that followed the first 2 and failed the third one, and that was the harmonic series, 1 plus 1 over 2 plus 1 over 3, and you just kept going to infinity. That one actually diverges when you take that integral test. You can quickly analyze. Without doing that, you can do what we call the p-series. And the p-series is if you got 1 over n to the p. If p is greater than 1, like 1.00001, then it's going to diverge. If it's less than, or I'm sorry, converge if it's greater than 1. If it's less than 1, it's going to diverge. So for the p-series, if it's less than 1, like 1/2, or 1, it's going to diverge because it's harmonic or less. If it's greater than 1, like 1 over n squared, 1 over n cubed, those will converge. So be aware of that p-series. Another exception is the limit comparison test. They'll tell you, use the limit comparison test. Take 2 functions, one series that you know about, one you don't. Let's say one of them converges, and you know that. If you do a ratio test, limit as k approaches infinity of a of k over b of k. If you get a constant not equal to 0 or not equal to infinity, I like what they did, 0 to infinity, then you're going to have both converge or both diverge. So if you knew one diverged, they both diverged. If you knew one converged, you'd know they both converged. Those are all of the tests that we did. Then the last part I want to mention are the 3 errors. Okay? Not the 3 errors you'll make, but the 3 errors to consider. 3 errors are non-alternating condition. So what you do there for the errors is you just say the error is less than the integral from n, where you left off, to the infinity of u of n dn. Think of it this way. If you had a partial sum, you did something like this. The actual true sum is going to be the partial sum, like 1, 2, 3, 4, 5, plus the error. That's how you would find that sum. Another way to find a non-alternating sum is the geometric series. A over 1 minus r, we love that, geometric. And then the third one that we did where we actually found the sum was going to be with the telescoping. That was a partial fraction. I can go over that if you want to some other time. And then the alternating series and the Maclaurin and Taylor both have the same thing. They would go, your error is a little bit less than the next term. Same thing with this one. The error was a little less than n plus 1 of c x minus a to the n plus 1 over n plus 1. But it's still the next factorial, still the next term. C is either going to be 0 or c is either going to be x minus a, whatever gives you the most error for that. And those are the three errors. Non-alternating, you just go from whatever you left off from the partial, like 5 to infinity, and the error is a little less than that. Alternating, you're going to go the next term, and the same with Maclaurin-Taylor. Don't forget to check 0 and x minus a. That's series.